And thank you everyone for being here. It's really exciting to be part of the Reactive Summit this year and have the ability to share with you how we've actually been embracing Akka Streams in order to unlock the power of a valuable workflow here at Adobe. So I'm Bianca. I'm a software engineer for Adobe, working here for almost 4 years. And for me, Reactive Summit is really a special one. The first time I attended it was 3 years ago. It was my first time in US, first time starting with a new team in Adobe, with a new project, and really trying to use my passion for functional programming, Scala and Akka Internal in order to start building projects using them, but also um, making my team colleagues embracing them as well. And back then, there was this talk of Stefano Bonetti on how to design your streaming data pipeline using Akka Streams. And since then, it kind of became my reference talk. Not only did it enable me to have a really fast bootstrap into getting hands-on with Akka Streams, understanding the basic concepts, but it also provided me kind of a boarding track to use with my colleagues as well. So thank you, Stefano, for that presentation. And yeah, it's exciting to be on the other side of the stage this year and have the ability to give something back to this amazing community. Now, regarding what we do here at Adobe, the use case that I'm going to present today is really centered around Adobe Real-Time Customer Data Platform, whose sole mission is to help marketers understand better their customers and activate efficient campaigns. If we take a look at the data flow angle, there are three main building blocks that facilitate all the capabilities that this platform provides. Firstly, we're talking about data collection and how data comes into Adobe platform, be it from user real-time interactions on their mobile apps or web browsers, integration with third-party systems that publish this data to Adobe. And at the end of the day, by using deterministic and non-deterministic algorithm, this data is stitched together in order to provide a single unified profile view of the end user. And having this capability, marketers can apply different rules, can split their audiences in relevant segments. And then the most valuable part is the fact that this data doesn't stick only to Adobe internal systems, but marketers can also activate this data by exporting it to various third-party integrations. My team has actually been involved in this activation piece, the one that takes all this process profile data and uses several connectors in order to export data to partners like social media ones, Facebook, LinkedIn, or Twitter. And the main use case that we've been building is by leveraging an HTTP connector. And because the data that is flowing through the real-time customer data platform is really at high throughput, we've set ourselves rather high KPI of being able to transport over 1 million profile updates per second, and also take into account that each such integration is a peculiar one. When it comes to the API integration, what is the format of response, how data is actually being translated from what Adobe stores to that third-party systems, and also having in mind that regardless of the integrations, we have to provide the same guarantees to our customers, provide that data really fast without being affected by potential erroneous integrations. And to deal with such challenges, we have chosen to use Akka Streams, whose sole mission is basically ours as well, to be able to handle unbounded data volumes and at the same time use our resources effectively in order to not overwhelm our systems and meet our performance KPIs. When I firstly thought about sharing with you our journey, because it has been actually a journey, I wanted to provide the angle of what it gets to having one team, because there's always about the team, and what it takes to actually adopt such a reactive streams implementation and roll out different applications that perform your required business logic and roll them out to production. At first, there's the momentum of understanding the real basic concepts and get some hands-on experience. Then after you perform this exercise for a bit, you start to actually take a look underneath and understand what it works for you best. And then before considering that application really production ready, you would need to take a look at the performance. And this is what I wanted to share with you today, how we actually went through step by step in this journey. So how we actually started from with a team with little to zero actually Scala and Akka knowledge. We got a really simple, let's say, bootstrap project. Our sole mission at the beginning was to just get some hands-on experience while consuming profile updates from a Kafka topic, apply some business logic, and then land that data somewhere by HTTP. And whenever dealing with streaming application in general and adopting such a framework, the first thing that it comes really natural is to go to the drawing board and really start sketching how it looks, your graph processing when it comes to the business logic. And luckily, Akka comes to help you even from the design phase by just starting to understand the basic building blocks that make up the framework. You always have a source of data from which you can get the actual incoming events. Then you have several nodes, which are called flows, that are responsible for applying different business logic. And then the process data lands into a sync. So having this simple goal in mind and starting leveraging the building blocks, and also the fact that this framework is statically typed one, we could actually start sketching our application on the drawing board. We had a source of incoming messages. Those messages would further need to be transformed to profile updates, and those profile updates would need to be dispatched by HTTP. And even from this simple design phase, the next step that we had to consider was what happens when something goes wrong. As Jonas was mentioning in the keynote before, it's really the momentum when you need to actually start embracing failure and how to design your application to cope with that. And luckily, both Scala and Akka helps you with that. For instance, the most basic example that we could use in order to prepare ourselves for failures was considering the fact that some incoming messages would fail some validation constraints. And rather than actually dealing with those errors by throwing exceptions, producing unwanted side effects, we've actually gone to transform those errors into events. And for that, we've leveraged Scala type system, which already provides either, which has been actually designed to deal with such a use case, a data type that would let you encapsulate either a result, a successful result, or a type of failure. And at the end of the day, the flow of transforming the incoming message to either such an error event or a profile update would be quite straightforward and generic. Besides that, the power of Akka Streams is the fact that besides the basic concepts of using a source or flow or a sync, it actually gives you the freedom to draw any shape that you would like. So starting from a flow shape with one single input port and one single output port, you also have the capability to choose whatever number of input or output ports are working for you. In our case, we've chosen to actually have two output ports in this case. And then whenever we encountered such a validation constraint error, we would defer that those failures as events to another type of sync, so that we wouldn't affect the main processing pipeline, but we would still be able to asynchronously deal with those types of failures. And this could be easily extended for each such stage where things could go wrong. And we've adapted it in this way so that each processing step would actually provide such an either type. And at the end of the day, you could think of this specialized sync error as simple as you would need it. For instance, you could either log these errors to a separate log file, you could define some alerts based on that, or even connect those errors with the data letter queue and have another downstream system in order to deal with them. But the most important thing and takeaway from here would be the fact that still the main processing pipeline wouldn't be affected by such erroneous events. And just by looking at this drawing piece, we could actually go to writing code straight away, because the framework really is really developer friendly in this way. If we take a look at the right drawing piece, we can actually understand what is here. Each Akka Streams application is actually a graph or blueprint at first, which you can easily translate from the drawing board to actually leveraging the API. And then that blueprint is being materialized whenever you have the resources available and you actually run the application. And this is where the magic starts. So by using the API capabilities and having this straightforward onboarding, in order to be able to roll out really fast other applications, because we had to build different microservices in order to deal with different capabilities throughout our data plane, we needed to have a way to leverage the learnings from our pilot project in order to be able to write and deploy a new application really fast. So to do that, we've actually designed our applications in order to be configuration driven. Because at the end of the day, using a Kafka source or an SQS source or whatnot, or a different sync, could be as easily as just changing a configuration value here, and then just leverage a common SDK that our team would maintain and enhance by using Alpaca connectors, also setting up some generic metrics, and so on. So by using this this design approach, from starting with 0 applications, our team has actually managed in several months to maintain more than 10 applications in production using Akka Streams. And the takeaway here is the fact that starting from the composability that the actual framework provides and designing the applications to be configuration driven, we've actually been able to leverage this design pattern to have a way of leveraging generic reactive layer stages, and whenever designing and implementing a new application, to only be concerned with the business layer. Now, the next step in our journey was to actually start deep diving into what are the real capabilities of the framework and really prepare for our performance KPIs. And the first thing that we needed to do as a team was to actually understand what is happening there behind the scenes. And the entry point here is actually understanding what is happening at runtime. Whenever you run an Akka Streams application, what is happening behind the scenes. So Akka Streams is actually an implementation that leverages Akka, which is an actor model implementation that has been built for message-driven applications and to deal with concurrency without taking care of low-level details. So if we take a simple application like this one, having a source of incoming events, transforming those incoming events to some meaningful data types and then dispatch them somewhere, all these stages will be actually part of one single actor responsibility. At runtime, this would mean that all these steps would be performed sequentially on the same thread. Now, if we think about more complex graph processing use cases, when we deal with the CPU-bound workloads or IO-bound workloads, it would be ideal to have different segments of the streaming application separated in order to make sure that you saturate and use effectively your resources by keeping both or the multiple segments busy with performing some work. And to deal with this, you can actually introduce asynchronous boundaries between such segments of streams. And this is really simple just by adopting the async keyword and put it whenever you want to separate such segments of interest. When this happens, Akka Streams behind the scenes actually decouples those segments by leveraging different actors, which can then be configured in order to use different thread resources so that those segments are really performed under different contexts. And asynchrony cannot only be achieved by having this boundary. There is often the case like we had to perform an external communication, let's say with another microservice. Ideally, this communication could be wrapped in a feature that would either be completed on a different thread or even in, under a different execution context, depending on the resources. And this can be leveraged by using mapAsync, which is configurable with a specific parallelism parameter. In this way, you can actually make sure that the first segment is busy with fetching data and performing transformations, while the other segment is actually dealing with the external communication. And what is important to acknowledge here at this step is the fact that mapAsync, as it comes, it preserves the order. And this is really important because this means that whenever a feature is completed, the result cannot be passed downstream as long as the preceding feature hasn't been completed yet. And this might be tricky when you're actually dealing with a rather non-uniform workload. In our case, we needed to perform several HTTP requests, and sometimes some requests would be more beefy in terms of payload and requirements on the other system. So we would have results in milliseconds or even seconds. And if you don't care about the order, you can actually use mapAsyncUnordered to make sure that whenever you have a result available, you can just pass it downstream. However, in our case, we care about the both. We wanted higher throughput, but still we cared about the order. And luckily, Akka Streams helps you with that as well. As I was mentioning before, whenever introducing async boundaries, by default, there's a buffer introduced between those segments so that the overhead provided by the communication required between those actors, in order to make sure that doesn't bring an overhead in your throughput, Akka actually uses a buffer between those segments, which by default is configured to 16 elements, so that the segment downstream can still fetch from that buffer without actually bending on the upstream to provide data. Doing so, you can even extend that behavior by using explicitly defined buffers so that you can accumulate even more data between those segments of interest. In our case, we have increased the buffer to be of order of thousands because we wanted to make sure that the upstream segments are still able to effectively use the resources and perform some work, while this communication segment would still be able to deal with this non-uniform workload. And this has proven itself really valuable in our workflows, and we'll see later on that this has also helped us when tweaking our performance parameters. The last important aspect that we needed to actually start understanding more is also is regarding error handling. We've seen before that both the language and the framework provides capabilities in order to embrace failure as events and deal with them in a contained way without affecting the main processing pipeline. However, there are cases where you actually might need to cope with it in a different way. In our case, we were using a custom Kafka API in order to retrieve data from Kafka cluster managed by one of our teams. And whenever something went wrong with this communication layer, we would receive an error. Of course, we could still design this part in order to transform this error into yet another event type. However, we wanted to be notified or be able to react whenever this communication error was not a transient one. So the simple thing here would be to just throw the exception and let the stage stop and eventually the stream stop so that we could further act upon it. However, we still wanted to be able to let the application crash and perform some self-healing before actually requiring some manual intervention from our side. And luckily, Akka Streams has this capability as well. It inherits what is called supervision strategy from Akka, actor model. And this deals with the fact that when designing hierarchies or actors, you can always define supervision strategies for parent actors to help child actors when something wrong goes with them. And there are three main supervision strategies that can be triggered whenever such a runtime exception is triggered. You can either restart, stop, or resume the actor. The same way it works with Akka Streams. You have the ability to define a supervision strategy for a specific stage or for the entire stream. In our case, for our custom source shape, we've chosen to use a restart strategy so that whenever we encounter the communication error, the, the supervision strategy would be triggered and would automatically restart the resource with the backup mechanism. And this way, we ensure that the application is still self-healing and being capable to deal with failures without affecting the main pipeline. However, we still wanted to account for communication errors that were not transient and that would actually produce some latencies on our side, because for each backup introduced, this would mean on our side that we are not being able to consume data and process it. And it would violate the KPIs that we need to provide with our services. So for that, we have chosen to go with the maximum restart so that after some time of having the application still trying to connect with that Kafka API, to actually let the stream stop. And what we actually wanted to make sure when this happened was the fact that we wanted to avoid data loss at any cost, because whenever dealing with different segments of processing using the synchronous boundaries, this would mean behind the scenes that some in-flight elements, events in our case, might still be there when stopping the stream. And we would like to firstly consume and process those events and then stop the stream entirely. And for this, we have leveraged the kill switch mechanism that Akka Streams provide, which is rather marker that you could introduce in your streaming application before each such critical segment. And by calling this in a coordinated shutdown hook, the stream wouldn't stop unless the upstream and would be canceled and the downstream would be completed. And because we are deploying our applications with Kubernetes, this has become really natural to tackle. At first, the application would try to heal by itself. When the maximum number of restarts would be exceeded, then the application would stop, the pod would be recycled, and after a specific rate of restarting pods, we would be notified via an alert and would require some manual intervention from our side, coordinate with the team that maintains that Kafka cluster in order to deal with this communication error. But at that point, the application would still be able to deal with errors by itself, which brings my mind back to the previous keynote, that we still need to design for resilience inside the app first, and then leverage the mechanisms that we have in our infrastructure providers in order to make the next steps in this direction. And this, again, has been a critical step in our journey to adopting Akka Streams. And because we've actually gone through this journey and understood the most important concepts for our use case, because the framework is really rich in terms of capabilities and configuration tuning that you can do. But for ourselves, all these have proven really valuable. And before actually considering our first production ready application, we started to actually dig into what it takes with our infrastructure to and the design of our applications to deal with and meet our KPIs. And we started with the same simple application, but adding some required lookup mechanism in order to fetch some data from an external endpoint and enrich those events. And our KPI was still the one that I mentioned before, 1 million incoming events per second. And we started with just deploying one pod in production using our performance test generator and see how it performed. And to our surprise, the rate was actually 60K coming events per minute. So to be able to cope with our initial KPI, we would need about 1,000 pods, which would also imply 1,000 Kafka partitions. So this really didn't look pretty well. So that was the moment when we actually started to dig into what is under the hood of our application. And the first natural thing that we've done was to actually eliminate all the business processing steps and identify whether even the source was actually providing a bottleneck into meeting our KPI. So we actually took out all the business steps. We just connected our custom source that was fetching data from Kafka, and we were leveraging no operation sync in order to just measure the throughput of this one. And by measuring this again with one single pod, we've actually discovered approximately 10x improvement in the throughput. So that was the moment when we actually eliminated this as a bottleneck and transformed this as a baseline, what it would take for the downstream steps in order to maintain this high throughput compared to the initial one. Intuitively, because the lookup stage would require external communication, we started to add parallelism there and increase those values, tested with different infrastructure resources in terms of available cores and different parallelism configurations. And after performing the same performance test, we've actually started to notice the initial throughput of the source reaching almost 800K per minute. But then what was interesting was the fact that still at some point, it would decrease to about 500K. And this indicated for us that somewhere downstream, some buffers are not being filled. Back pressure would come in, and this way we wouldn't be able to fetch data from the source at our expected rate, because a downstream stage would still be busy and we would not be able to consume our resources effectively. And in that respect, we've actually started to introduce asynchronous boundaries between each two stages. And we actually added metrics before and after each such buffer in order to account for what goes in and what goes out for each processing step. And as you can see in the drawing board, there are some colors that are actually reflected in our test results. And just by looking here at the available numbers of how many elements we had in a respective buffer, we could see that the first stages would be able to consume a high number of elements. However, at the serialization step, before and after it, we would see a smaller throughput. So this indicated the fact that the serialization step would be the bottleneck. And what we've done here we just increased the parallelism here as well, tested again with different configuration values and resources, and we got in the end with almost the initial source throughput, 700K per minute. So just by doing this simple exercise, we've been able to reach to a 10x improvement and really use our infrastructure resources in a more effective manner. What is also important in this journey is the fact that we wanted at first to make sure that we understand by ourselves what is under the hood and understand what metrics we need to collect. So for that, we have refrained ourselves from using different platforms to help us right away, but rather we've leveraged the tools that we've been using for other projects. We use the same deployment model. We use the same monitoring stacks that we've previously done. So there was nothing Akka specific, but rather we wanted to understand first what's behind the scenes. And this has been really helpful for a team like ours. Now, our applications are a bit more complex than what I've got the chance to show you today. However, I hope that I've managed to convey the message of how important it is to actually start from a business use case, understand what is your end goal, what is the infrastructure capacity that you would want to deal with it, and then start to deep dive into the framework, understand the concepts that you deal with, and then test both your application and infrastructure setup. So thank you for being here and looking forward to your questions.